In this video, we want to show how an asynchronous counter can be used as a frequency divider. So we have a 3-bit asynchronous counter. Since it's asynchronous, we will draw the connection first, connection diagram. So this one is the system clock, and they will have different clocks, each of the flip-flops. So this output Q0 goes as clock of the second flip-flop. If we call this flip-flop 2, this is flip-flop 0, this is flip-flop 1, 0, and then 2. And Q1 goes as clock of the flip-flop 2. So that's how the connection will be. And all of the flip-flops will be in toggle mode, so we have to give 1 in the T inputs, at the T inputs. So that's there, and we have. So now what we will do, first we will draw the wave shape. So let's say this is the clock signal, like that, and we have, as the drawing, as per the design, this is a rising edge clock, all of the flip-flops. So this will be the clock edges. These are the clock edges. So we can start from any any output situation. Let's say all of them were 0, and if this is our clock signal CLK, then we want to draw Q0. Let's say Q0 was 0 initially. With this clock edge, the first one, it will go 1 here, then again the clock edge is here, it will go down. With at each of the clock edges it toggles, so like that, and so on. So what happens is, here we notice that this is one time period of one clock cycle, but here the time period is up to there, and it has doubled because this is 2 clock cycles here, and this is 1 clock cycle. So time period has become double, the frequency has become half. So if the frequency of the clock was f, this one's frequency is f over 2. Now for this flip-flop, the flip-flop 1, Q0 is the clock, so we will write the clock edges, and this one's clock edge is again rising edge, so these are the clock edges. And if Q1 starts from 0, here it becomes 1, then here it goes down, here it goes up again, goes down again, goes up. And again what happens, we notice that this is 1 clock cycle. I don't know, maybe a different color. This is 1 clock cycle, one full cycle, and this is twice of the previous one. So here the time period, here it is, this one is 2 cycle up to there. So the time period has become double again, so frequency has become half of that. So this one's frequency will be f over 4. Time period, if it was t, this has become 2t, this has become 4t, like that. So if this is t, this one is 2t, and this one is 4t. Finally we have Q1. This is our Q1 here. Q1 is the clock cycle for flip-flop 2, clock signal for flip-flop 2. So these will be the clock edges here, just 3 of them. And if Q2 also starts from 0, it goes 1 here, then up to there it is 1. Here it toggles again because this is where the clock edge comes, goes down, and then again here. So 1 cycle is up to there, which is 2 of this this signal. So that means again time division, time period will be 8t, 2 of 4t, so 8t, and frequency has become f over 8, half of this one. So this is how it can be used as a frequency divider, the 3-bit counter. And if we want to, let's say, get 1/16 of the clock signal, then we will need 4 stages. Here we have got 3 stages of 3-bit asynchronous counter basically. As a result, the frequency of this is 1/8 of the original clock signal. If we had another stage, if it were a 4-bit asynchronous counter, we would have got 1/16 f of the, or 1/16, the frequency would be 1/16th of the original clock signal. So that's how we can use it as a frequency divider.